The Langmuir-Hinshelwood kinetic expressions are commonly used to describe the reaction rates for heterogeneously catalyzed reactions. This expression is named after Irving Langmuir, Nobel Prize Chemistry 1932, and Cyril Norman Hinshelwood, Nobel Prize Chemistry 1956. To take just one example, for zeolite catalyzed isomerization of 2-methylpentane to produce 2,2-dimethyl butane, the reaction rate expression is written in this form, where we have the numerator that contains the forward reaction rate constant times a partial fugacity of component 1, 2-methylpentane, in the bulk fluid phase, minus a reverse reaction rate constant, K reverse, times the partial fugacity for component 2, 2,2-dimethyl butane, in the bulk fluid phase. And the denominator is a term that contains 1 plus B1F1 plus B2F2, where B1 and B2 are absorption constants describing the binding strengths of components 1 and 2. My objective today is to go through the derivation of the Langmuir-Hinshelwood kinetic expression. For further background on the theory behind this derivation, I refer you to my publication, and also view my presentation on the ideal adsorbed solution theory on my YouTube channel. We start our derivation of the Langmuir-Hinshelwood kinetic expression by considering adsorption of a single component and a binary mixture in porous adsorbents, and thereafter we consider reaction rates and the derivation of the Langmuir-Hinshelwood kinetics. We start our discussions by considering the adsorption of a single component in a porous adsorbent. The porous adsorbent is considered to be made up of M adsorption sites, and we may write the rate of adsorption to be proportional to the number of vacant sites within the material. Since there are a total number of M sites, the total number of vacant positions that are available for adsorption is equal to M times theta V, where theta V is the fractional vacancy. F is the fugacity of that component in the bulk fluid phase surrounding the adsorbent, and K adsorb ADS, K adds, is the reaction rate constant for the adsorption process. The fractional vacancy may be written as 1 minus theta, where theta is the fractional occupancy, and so there are the occupied sites are indicated by these red circles here. The vacant sites are available for adsorption. The the rate of desorption is proportional to the number of occupied sites, which is m, the total number of sites, times theta, the fractional occupancy. And K DES is the reaction rate constant for the desorption process. At equilibrium, we may equate the rate of adsorption to the rate of desorption and derive an expression shown here. K adds times F, the partial fugacity in the bulk fluid phase, divided by K desorption, and the ratio of the adsorption rate constant to the desorption rate constant can be termed as a binding constant B. So B times F is theta divided by 1 minus theta. This expression may be rewritten to explicitly relate the fractional occupancy to the partial fugacity in the bulk fluid phase, and this expression is shown here, where the partial occupancy or fractional occupancy is the molar loading Q divided by Q sat, the saturation capacity. And we have the familiar expression for the Langmuir isotherm. We can generalize this for a binary mixture in the following slide. For a binary mixture of components 1 and 2, component 1 shown in red, component 2 shown in blue, on a heterogeneous adsorbent containing a total of m adsorption sites, the rate of adsorption for component 1 can be written in the following form, in which the rate of adsorption is proportional to the partial fugacity of component 1 in the bulk fluid phase times the number of vacant sites, and the number of vacant sites is m, the total number of sites, times the fractional vacancy, and the fractional vacancy is 1 minus the occupancy of component 1 minus the occupancy of component 2. The rate of adsorption is balanced by the rate of desorption of component 1, and the rate of desorption of component 1 is proportional to the occupancy of component 1, shown by the red circles in this schematic here. So by equating the rate of adsorption to the rate of desorption, we derive an expression B1F1 equals theta 1 divided by 1 minus theta 1 minus theta 2. And precisely analogously, we can write the expression for the rates of adsorption of components 2 and desorption of component 2, and we derive B2F2 equals theta 2, which is the fractional occupancy of component 2, divided by 1 minus theta 1 plus theta 2. If we add this term to this term, we will derive this following expression: 1 plus B1F1 plus B2F2 is 1 divided by 1 minus theta 1 minus 1 theta 2, and this is the fractional vacancy. And therefore, the fractional occupancy of component 1 is B1F1 divided by this term here, And the fractional occupancy of component 2 is B2F2 divided by this term 1 plus B1F1 plus B2F2. We have now the expression to describe the fractional occupancies θ1 and θ2 of components 1 and 2. And on this basis, we can determine the molar loadings of components 1 and 2, which are Q1 and Q2. For further details, see my presentation on IAST on my YouTube channel. Having this background, let's consider the derivation of the Langmuir-Hinshelwood kinetic expressions. Let us set up the kinetic expressions for alkane isomerization using MFI catalyst. We consider the isomerization of 2-methylpentane to 2,2-dimethylbutane. Both components are preferentially adsorbed at the intersections between straight and zigzag channels. Per unit cell of MFI zeolite, there are 4 intersection sites, and the unary isotherms for 2-methylpentane, shown in blue, and 2,2-dimethylbutane, shown in yellow, which is represented here. These show a saturation capacity of 4 molecules per unit cell. So the saturation capacities of both components are equal to each other. The molar loadings of components 1 and 2 in the adsorbed phase are described by the expression derived in the foregoing slide for binary mixture adsorption. So Q1 is equal to the saturation capacity for component 1, corresponding to, say, 4 molecules per unit cell, times the adsorption constant or binding strength for component 1, B1, times the partial fugacity of component 1 in the bulk fluid phase. And we have the denominator, which is 1 plus B1F1 plus B2F2. Similarly, Q2 can be written as being proportional to B2, the binding strength for component 2, times F2, the partial fugacity of component 2 in the bulk fluid phase. The reaction rate is written as K1, a forward reaction rate constant, say, times the molar loading of component 1 minus K2 times Q2, which is the molar loading of component 1 in the adsorbed phase. This reaction rate has the expression as the units of moles per second per kilogram of MFI catalyst. By substituting the expressions for Q1 and Q2 in here, we derive this expression, from which we have K forward times F1 minus K reverse term F2 divided by this denominator term, which contains the binding strengths of component 1 and component 2. This derivation makes it clear that the Langmuir-Hinshelwood kinetic expressions that are commonly used is applicable, say in this case for binary mixture adsorption, where the components 1 and 2 have equal saturation capacities, and the expression derived in the previous slide for binary mixture adsorption is valid. This expression is not always correct for mixture adsorption when the saturation capacities of the species in the mixture are different. The ethylation of benzene to produce ethylbenzene is an industrially important reaction that is catalyzed by MFI zeolite. The dehydrogenation of ethylbenzene results in the production of styrene that is a feedstock for producing polystyrene. The reaction rate expression is written in this manner, in which the forward reaction rate is proportional to the product of the adsorbed phase loadings of components 1 and 2, and the reverse reaction rate is proportional to the molar loading of ethylbenzene within the catalyst. So how do we set up the proper expressions for Q1, Q2, and Q3? One way to do this is to write a generalization of the multi-component Langmuir model for mixture adsorption, in which the molar loadings are written as being proportional to the saturation capacity of that component times an adsorption rate constant B sub I times the partial fugacity in the bulk fluid phase divided by this term, which is 1 plus B1F1 plus B2F2 plus B3F3, where B1, B2, and B3 are the Langmuir constants that are derived from the unary isotherms. However, this expression for mixture adsorption is thermodynamically inconsistent, and a more general approach and correct approach is to use the ideal adsorbed solution theory to calculate the molar loadings of components 1, 2, and 3. The details are provided in my publication cited here. See also my presentation on IAST on my YouTube channel. The message I wish to put across in this presentation is that the Langmuir-Hinshelwood kinetics that is commonly used in practice relies on an expression for the component loadings that are not precisely correct thermodynamically speaking, and in practice it is preferable to set up the expressions in which the reaction rate is written in this form and the component loadings Q1 and Q2 and Q3 are determined using the IAST.